Welcome back, students. Last class we talked about relations and functions, so just a quick review. Relations are a list of ordered pairs, and functions are relations that do not have any repeating x coordinates. So today we're going to talk about a specific kind of function, and these are going to be called linear equations. So why are they called linear equations? Well, simple enough. Their graphs are always going to be lines. All right, so what you could always do to tell if you have an equation that is linear or not is graph it. Okay, is the graph a line? Yes, it's linear. No, it's not. But you might not have a graph in front of you, so what are some other ways we can tell that you are going to have a line if you were to graph it? All right, just a little bit of information about linear equations. They are said to be of first degree. To determine the degree of an equation, you look at the variable and you look at the highest exponent that is used, the largest exponent that is used. All right, there is going to be no exponent other than 1 on any variable if this is going to be a linear equation. So that's why these are going to be called first degree equations. Also, there can't be any multiplication of variables, there can't be any variables in the denominator, and there can't be any variables under a square root. If there were, all right, so y equals x, there's the parent graph of a linear equation. Okay, let's go back and talk about those rules a little bit more. If we had an exponent other than 1, so right now y and x both have exponents of 1. If we had an exponent other than 1, let's see what that would look like. All right, so x squared, we have a parabola, x cubed, x to the 4th, x to the 20th, or x to the 1/2, and so on. We'll study all of those graphs here second semester. All right, so remember, has to have variables with exponents no larger than 1. You can't have a multiplication of variables. So what if we had y times x is equal to 3? The graph is not a line, hence not linear equation. What if we have y equals, we can't have a variable in the denominator, so what if we have y equals 3 divided by x? Again, graph is not linear. And the last rule was we can't have any variables under a square root. So y equals, put a square root, and then I'll put x. Again, the graph is not linear. All right, so what we could do is we could graph each one of these to determine whether or not it is linear, or we can just see, are we breaking any of these rules? And if so, the graph's not linear. If we aren't, then we do have a linear function. All right, so we have f of x. Remember, that's just function notation. Don't think that you're multiplying variables here. F is not a variable. It is the name of the function. X is the input. All right, so we have, I'm just going to be looking over here on this side. Okay, we have x over 3 plus 2. So here we have a variable. It's to the first degree. There isn't any multiplication of variables. We do have a denominator, but we don't have a variable in the denominator, so we're okay there. And we don't even have any radical signs. So that means that, yes, this would be a linear function. For the next one, we have variables. We have them to the first power, so that's good. But we have a denominator, and we see a variable in the denominator. So no, this is not going to be linear, again, because we have a variable in the denominator. This one's okay, this one's not. And for the last one, we have p of x is equal to negative x to the third minus 9. So right here we have x to the positive third, which means that we have an exponent other than 1, which means that no, this graph is not going to be linear. All right, so I'd said something before. I said y equals x is considered the parent graph. Okay, this is the most basic linear equation that you can have. Now we can do some modifications to this equation, and we can see some changes, some transformations in the graph. One transformation that we can see is right now we have y equals x, but what if we put a negative in front, and we're going to see that the graph, instead of going up when we read from left to right, because we read sentences, we read untitled graph, I read that from left to right. So when I look at a graph, I go from the left side to the right side. So now when I put a negative in front, the graph is going down. When it was positive, the graph is going up. I could put numbers in front of it and I see how it changes. So it's still going up because it's positive. All right, but now it's gone from going only up 1 to the right 1. Now I put a 2, so now it goes up 2 over 1 and so on. All right, other options for what graphs could look like, other transformations. We could put a number at the end. So I could add +3. I could put a -2. Okay? And we're going to see that how we go up and over doesn't change. All that's changed is we shifted the graph up or we shifted the graph down. So if I put a +3, now instead of the y-intercept being at the origin, now it's up at 3. Or if I put a -2, now the graph is shifted down and the y-intercept is down at -2. All right, something else that we could do is we can actually get rid of a variable. We can have y equals 5. And we have a line still. It's just that this line goes straight across. It's saying that everywhere y is 5. You can change what the x values are, but y has to be 5. So we're talking about, okay, just going left and right, not going up or down any. And we can also do the same, but have x equals. So we could have x equals -2. Right, and then this is just going to be a vertical line. So this one actually would not be a function because we'd have repeating x values. All of the other lines that we've looked at would be functions. All right, so what I was focusing in on changing there, I know I did some other transformations, but what I was really trying to show was that we can have 4 types for what our slope is going to look like. All right, so slope, just as a reminder, is your rate of change. That's your change in y's over your change of x's. It's your rise over your run. This is your formula. M equals y2 minus y1 over x2 minus x1. All right, so we have 4 possibilities. We could have a graph that goes up from left to right. All right, so what makes it so it goes up from left to right is the fact that what's in front of that x, that slope, it's positive. All right, so that m is going to be equal to a positive number. And the graph is going to look like this, where it increases from left to right. Try to put arrows on it. Sorry, this is hard to do. Okay. Another option that we have is when we put the negative in front of that x, we have a negative slope. And what happened was the graph switched. Instead of going up, it then ran down from left to right. So the slope is negative when the graph looks like this. And then we also got rid of a variable. All right, so let's go back to this one where we had y is equal to 5. All right, so if we're talking about change in y's, well, this is saying y is always equal to 5. So there is no change in your y values, which means that your slope is equal to 0. All right, so the slope is equal to 0. And again, that's always going to be a horizontal line. It only goes through, the equation of it was y equals a number. It only goes through the y-axis. And then the last possibility that we have is when we have what's called m is equal to our slope is undefined. Now, why is it undefined? Well, because we're going to have lines where we have x equals a number. All right, so this time it's saying that the x is always staying the same and the y values can change. So if x values stay the same, we're going to have a number minus itself, and that's going to be a divide by 0, which is not possible. All right, we are never able to divide by 0. All right, so that's just going to be anytime you have a vertical line. All right, so 4 possibilities with slope. Again, slope, the formula for it is right here. Okay. So now let's take a look at an example involving your rate of change or your slope. All right, so it says in 2013, 30,955 students applied to Purdue University. And then in 2016, 47,475 students applied. Find the rate of change of students applying for admission to Purdue from 2013 to 2016. All right, so first thing that you should do, okay, word problems always seem to be a little bit harder rather than the straightforward find this, do this, and so on problems. All right, so first thing that I would suggest that you do in a word problem is read through it all the way and then go back and pick out the numbers. So here we have 2013, we have this number, we have 2016, we have this other large number. What do these represent? So 2013 represents a year. 2016 also represents a year. 30,955 represents how many students applied, and this number also represents how many students applied. All right, so that means that we have two variables. We have a year, and we have how many students apply. So I want you to pause the video, and I want you to think to yourself, which one's going to be the independent variable? Which one is going to determine the other one? All right, I hope you answered that the year is the independent variable, and the reason being is because the year is going to determine how many students apply. All right, so think back to when Purdue first started. I have no idea what year that would have been, but it would have been a while ago. So think about the early years. Would you have nearly this many students? Absolutely not. If you see pictures from when Purdue was first created, their campus has at least doubled, if not tripled, in size. So that means that they wouldn't have had anywhere to have all of those students before, so their numbers were nowhere near these numbers. All right, so the year is going to determine how many students apply, so that means that the year is the independent variable. The years are going to change no matter what, whether Purdue University exists or not. All right, so then what we're going to do is we're going to think of these numbers. So notice how 2013 goes with 30,955. So we're going to pair these together. These are going to be an ordered pair. We're also going to pair these numbers together and have an ordered pair. So what we're going to do is we're going to call this one, I'm going to change it to something that's a little easier to see. And again, I'm sorry about my handwriting. This is the independent variable, which means it's the x value. And this is the first x value that we're given. Here's another year, which means it's another x, the independent variable. And it's the second one that we're given. So we're going to use subscripts. So this was the first, this was the second. And then this is the y value that's associated with this first x value. So we're going to call this y1. And then here we have our second y value that's associated with our second x value. So we're going to call this y2. And so then to find the rate of change of this, we're just going to plug it into the slope formula that we have up above. So here's the formula. And now what I'm going to do is I'm going to replace in my formula what my numbers were. So instead of y2, I'm going to write that as the 47,475. Instead of y1, I'm going to replace that with 30,955. Instead of x2, I'm going to replace that with 2016. And instead of x1, I'm going to replace that with 2013. All right, and then feel free to use a calculator, and we are going to evaluate this. So we'll evaluate numerator, and we'll evaluate our denominator. All right, so using a calculator, I got 16,520 over 3, which is approximately equal to 5,506, which means that the number of students applying to Purdue increases by about 5,506 students per year. So now we're going to talk about the three most common forms that you're going to see linear equations written in. All right, there is technically one other form called general form, but we hardly will ever see that. So mostly you're going to deal with these three forms. So point-slope form, slope-intercept form, and standard form. So let's start off with point-slope form. And the reason I put this first might be because honestly, it is my favorite form. The reason why it's my favorite form is because it's easy to graph with, and you don't have to have a specific point in order to graph. All you have to have is any point that is on the line as well as the slope of the line. All right, so point slope form is y minus y1 is equal to m minus x and then minus x1. And notice that that is in parentheses. So this is all getting multiplied by that m. So m represents the slope of the line. Y and x are just variables, and then y with the subscript 1 and x with the subscript 1, those are a point that is on the line. All right, so here we have an example, of an equation written in point-slope form. All right, so we have y minus 2 equals negative 1/4, and then parentheses x plus 12. So the easiest part is to determine what the slope is. That's not the tricky part. In front of the parentheses, that's where the slope lies. There's m. All right, so the number in front of the parentheses would be negative 1/4. The hard part is trying to figure out, okay, what's the point on the line? Okay, the number part for it's easy. It's just going to try to be, what are the signs that I use? All right, so x is what's in the parentheses. So here's the number in the parentheses. We have a 12. And then y is what's after the y value here. So we have a 2. All right, now let's determine what the signs are going to be. All right, so what you're going to do is you're going to compare it to the formula. So here we have x minus, but here we have x plus. All right, so had it been a minus sign, it meant that this value would have just been a positive. However, this changes to a positive, so the only way that this could change from a negative to a positive is if we had a double negative. So remember, a minus minus we can't have. That's a double negative, which really means that we have a positive. So that means that this would have to be a negative 12. So if it changes the sign from negative to positive, you're looking at a negative number. If the sign stays as a negative, okay, it means that it was actually a positive. So negative 12 comma 2 is a point on the line. All right, so that is my favorite, because the way that I would go and graph this would be I would plot the point first. So I have a point at negative 12 and then positive 2. So I'd plot a point on my graph right there. And then the slope tells you how to move. So that slope was negative 1/4. So I go down 1 to the right 4, and there I would have myself a line. Slope-intercept form is probably what you're most familiar with, and it works really well too. All right, slope-intercept form obviously gives you the slope, and it also gives you the y-intercept. So m, the number in front of x, is still representing the slope, but this time we have the point. It still is a point, but it's a very specific point, the y-intercept, and that's the letter b that we use to represent the y-intercept. All right, so let me show you how easy it is to go from point-slope form to slope-intercept form. So here is our equation using our point that was given to us, not the y-intercept, but we can figure out what the y-intercept is going to be real easily. Now, how can we do that? Well, look at this formula, look at this formula. Y is by itself, y is not by itself. This has parentheses, this one doesn't. So all we're going to do is we're going to solve this equation for y. All right, so I'm going to solve this equation for y. So first thing I'm going to do is get rid of parentheses, because that's what order of operations tells me to do. So I'm going to distribute the slope in. So that's going to give me negative 1/4. And then negative 1/4 times positive 12 is going to give me negative 3. All right, and then last thing I need to do is to get rid of a minus 2. I need to add 2 to both sides. Can't add it to this one because this has a variable, so those are unlike terms, but I can take negative 3 and I can add 2 to it, and that's going to give me negative 1. All right, so just by solving for y, I'm now turning this into slope-intercept form, and I know the number in front of x, my slope is still negative 1/4, so this is still the same equation, still the same slope, just different forms, and now I know that the y-intercept, the b, is equal to negative 1. So I could write, instead of saying b equals negative 1, I could write that as an ordered pair. And again, to be on the y-axis, it means that the x-coordinate is 0, and that would be written as 0, negative 1. The last form we don't use that often. It's called standard form, and that's written as ax plus by equals c. A, B, and C are integer values, which means that they cannot be fractions. They have to be whole numbers. They have to be integers. And it's also most common to have A to be a positive value. Now, sometimes you're going to see A be a negative value, all right, but most commonly you're going to see A be a positive value. All right, now standard form is nice for getting the intercepts. So if I'm going to figure out what the y-intercept is, that means the x value, okay, that's going to be 0, which means that this goes away, and then I just solve this equation to figure out what the x-intercept is. This value would go away because y is 0, and then I solve that equation. So standard form is nice for getting your intercepts. The only other reason why I can really think we had standard form is back in a world of typewriters. Typewriters were really hard to type fractions with, virtually impossible, so that's probably why they created standard form, to get rid of the fraction values. All right, so let's work with what we have right here. So we have the slope-intercept form of the equation, and now let's turn it into standard form. All right, so there's the slope-intercept. To turn this into standard form, first thing that I'm going to do is I'm going to get rid of the fractions because we have to have just integer values. So remember what fraction means, okay? This is a division bar. That means divide. So we're dividing by 4 here. If we're dividing by 4 here and we want to get rid of that, we're going to have to multiply by 4. But to do something in an equation, you have to do it to everything. So I need to multiply every term by 4. So that means that I'm going to multiply y by 4. I'm going to multiply this by 4, which means it's going to get rid of my fraction. All right, so negative 1/4 or 1/4 of 4, you can think of as 1, and then we have the negative in front of it. Whoops, 1. And then 4 times negative 1 would give us negative 4. All right, so just like that, our fractions have now disappeared. And then now we want to get x and y on the same side, and we want to have the value in front of x be positive. All right, so here's x. I could leave it, and I could move y over, but right now x has a negative in front of it, so I want to make it positive, so I need to move it to the other side. So to get rid of a minus x, I'm going to add it to the other side, and that's going to give me x plus, and then 4y is equal to negative 4. So this would be my standard form. Now, the bad thing about standard form is the fact that I don't know what the slope is just by looking at this. All right, like I said before, the only good thing that comes out of this are getting the intercepts. So if I let y be equal to 0, that's going to give me that the x-intercept is negative 4. If I let x be equal to 0, it's going to give me the y-intercept is negative 1, because negative 4 divided by 4 is negative 1. I already knew the y-intercept from this form, but I guess the good news is I did get the x-intercept, which again was negative 4. So those are going to be the 3 main forms that we focus on for linear equations. Please be comfortable going back and forth between all of them or being asked to write an equation in a very specific form.